Welcome to the chapter on lithium dosing and drug concentration predictions. Lithium has been used for many years as an agent to treat bipolar disorder, but it also has other indications. The monitoring of lithium is interesting in that concentrations are generally monitored approximately 12 hours after a dose, and predicting that concentration represents several challenges. Lithium also exhibits multi-compartment distribution that may not be obscured by the absorption of the product chosen. However, since concentrations are rarely monitored shortly after an oral dose, this usually doesn't present a problem, as it might with other drugs like digoxin. Lithium can be a highly toxic drug if care isn't taken to avoid excessive concentrations. On the other hand, dosing adjustment is fairly straightforward if based on concentrations that represent steady-state conditions in a patient taking the medication as scheduled. In this video, we will estimate concentrations based on an administered dosing schedule and consider the impact of estimating average steady-state concentrations rather than a concentration measured 12 hours after a dose. I hope you enjoy the video on this interesting medication. Now let's examine what it might look like if we gave a dose of a drug that requires oral absorption but also demonstrates multi-compartment distribution. First, I'm going to plot the log of the concentration versus time rather than the usual concentration versus time, because it's easier to see the multi-compartment distribution if you plot it on logarithmic paper. So you can see the buildup of the concentration, the absorption portion of the curve, but then you see the distribution part as well. In this portion of the curve, not only is absorption ending and distribution going on, but the drug is also being eliminated until you get into the final elimination only phase of the curve. Let's try a patient case to demonstrate how we might dose lithium. We'll use a 30-year-old male patient who weighs 100 kilograms and who has a lean body weight of 80 kilograms and also an estimated creatinine clearance of 110 milliliters per minute. He's going to be given lithium for the treatment of bipolar disorder. What we want to do is predict the patient's average steady-state concentration if he'll receive 450 milligrams of capsules twice daily, and we'd use a 300 milligram and 150 milligram capsule to accomplish that. We begin by determining the pharmacokinetic parameters. One of the dosing approaches for estimating the clearance of lithium says that the creatinine clearance times 0.235 equals lithium clearance. Creatinine clearance in this method is given as milliliters per minute as well. So here in this case we would multiply the 0.235 times the patient's creatinine clearance of 110 milliliters per minute, and we'd end up with an estimated lithium clearance of 25.85 milliliters per minute. But we do need to convert that to liters per hour. So the way we do that is multiply the clearance in milliliters per minute times 0.06, which comes from 60 minutes per hour times 1 liter over 1,000 milliliters. Multiplying 25.85 times 0.06 gives us a clearance of 1.551 liters per hour. A second method of predicting lithium clearance states that the clearance in liters per hour is equal to 0.0093 times lean body weight plus 0.0885 times creatinine clearance. This time the creatinine clearance is in liters per hour, so we need to do that conversion first. And here we do the patient's creatinine clearance, 110 milliliters per minute, times the conversion factor of 0.06, which converts to liters per hour, and our final estimated lithium clearance, creatinine clearance is 6.6 liters per hour. Then we plug that into the formula for lithium clearance using first our lean body weight of 80 kilograms, and then the creatinine clearance in liters per hour of 6.6. And that gives us a lithium clearance estimated at 1.328 liters per hour. You can see that the two methods are slightly different in their prediction, the first method yielding a higher predicted lithium clearance than the second method. Now let's do some general calculations to estimate concentrations. The formula to predict CSS average is as follows. And the dose that we're using is 450 milligrams of lithium carbonate, but we need to convert the dose to milliequivalents, so we'll end up with the appropriate concentration, which is milliequivalents per liter. 450 milligrams of lithium carbonate equals 12.18 milliequivalents. When we plug the values into our formula, it's important to note that S is 1 for lithium. The carbonate part is not considered, it's already figured in. The F is 1. Bioavailability is considered approximately 1 for these products. The dose was 12.18 milliequivalents. The clearance for the first method was 1.551 liters per hour, and our dosing interval is 12 hours. That yields a predicted CSS average of 0.65 milliequivalents per liter on 450 milligrams of lithium carbonate twice daily. With the other method, the only difference is that the clearance is slightly less at 1.328, giving us a predicted CSS average of 0.76 milliequivalents per liter. Let's look at that on a graph. If this is our CSS average, about halfway between the peak and the trough, the first method predicted a CSS average of 0.65 and the second 0.76 milliequivalents per liter. Let's continue on. Lithium concentrations are generally measured about 12 hours after a dose at steady state for relating to the therapeutic range. Since CSS average is measured approximately halfway through the dosing interval, or 6 hours in this case, what we'd like to do now is predict the trough concentration at 12 hours using the two different clearance values and assuming that volume of distribution for the population is 0.8 liters per kilogram of lean weight. Let's determine the pharmacokinetic parameters. The clearance in the first method was 1.551 liters per hour, and we know that K is equal to clearance time divided by volume of distribution. That gives us K of 1.551 liters per hour divided by 0.8 liters per kilo times the lean body weight, which was 80 kilograms, giving us a K of 0.024 hours to the minus 1. For the second method, the clearance was 1.328 liters per hour. K again equal to clearance divided by V. We plug in our clearance of 1.328 and divide by volume and end up with a K for this method's approach of 0.021 hours to the minus 1. So let's calculate then what the concentration at trough might be based on the K that we came up with and the CSS average from both methods. We use the equation C equals CI e to the minus KT, where CI is the initial concentration and C is the concentration T times later. The CI for the first method was 0.65 milliequivalents per liter. The K was 0.024, and we're going down the concentration time curve 6 hours. The predicted concentration at 12 hours is 0.56 milliequivalents per liter, and compared to the concentration at 6 hours, it's only slightly less. Now let's do it for the other method using the same equation. In this case, the CSS average was 0.76 and the K was 0.021. That yields a concentration at 12 hours of 0.67. Again, not too much different than the concentration at midpoint. So the dosing changes based on these would hardly be different at all. Let's look at this pictorially based on one of the methods. That might be what a concentration time curve looks like. We drew a concentration at midpoint of 0.65 and at trough of 0.56. This is what we might expect to see.